Okay, so this is WebAssign 6D, or 6D, problem number 7. Okay, so we got a potter's wheel, a thick stone disc of radius 0.5 meters and mass 115 kilograms. It's freely rotating at 50 revolutions per minute. The potter can stop the wheel in 6 seconds by pressing a wet rag against the rim and exerting a greatly inward force of 71 newtons. Find the effective coefficient of friction between the wheel and the rag. So let's say this is the potter's wheel. This is spinning. And then let's say this is the pot. And then this is the hand with the rag. That's the rag. Okay, so it's spinning and it's applying a force this way against the side here. This is 71 newtons. The radius is 0.5 meters. Rotating 50 revolutions per minute. Okay. The potter can stop the wheel in 6 seconds by pressing a wet rag against the rim. Okay. So this is the torque unit, so obviously we're going to need to do something involving torque. And now what I'm going to do right away, actually, is find the moment of inertia, because that is more times than not what is necessary to solve a torque problem. So we're going to do that real quick. So what we're going to do is our equation, which is I is equal to 1/2 mr squared, because this is for rotating objects, mr squared. And we're just going to substitute what we have. So we have our mass, which is 115 kilograms, and we have our radius, which is 0.5 meters. So we're just going to plug that in right away. So I is equal to 1/2, was it 115? Yeah, 115 kilograms times 0.5 meters squared. So our I is going to be equal to about 14.3. So now I'm just going to extend the decimal point to 3, just so we can get a more accurate answer at the end. So kilograms times meters per second. So this is our I. And the reason we need this I, which is valuable for torque, and the torque is going to be valuable to find the actual amount of force being applied, meaning this 71 newtons times the coefficient of friction is the force that's actually applied, which caused it to take 6 seconds for the whole thing to slow down. So that's our I. Now here we're going to utilize, let me use a different color, torque equaling moment of inertia times angular velocity. And a common mistake here would be to plug in 50 revolutions per minute as our angular velocity, but the unit for angular velocity is radians per second, not revolutions per second. So we have to find 50 revolutions in radians per second, and all we're going to do is multiply the 50, let me do it on here, 50 revolutions okay. 50 revolutions a second times 2 pi, so our radian measure, over 60 seconds. So we're back in revolutions per second. That's going to equal 5.24 radians a second. But that is not what we plug in, because this is occurring over 6 seconds, not 1 second. So we actually have to find our change in angular velocity. And if we're starting at 5.2, it's freely rotating at, okay, let me use a different color. It's freely rotating at 50. Then we're stopping the wheel in 6 seconds. So if we're stopping, it's gonna be at 0. So our equation for the change in acceleration is gonna be initial minus final over time. It's going to be, no, it's final minus initial. Sorry. Final minus initial. It's going to be equal to 0 minus 5.24 radians per second. Make sure we're in radians. divided by 6 total seconds because it's happening in 6 seconds. And we are going to get a negative value here, which is fine. It's not going to affect anything really. Radians. Actually, my bad, it will affect it because this is actually it's slowing down, so it has to be negative. It's going in the opposite direction to slow it down. Okay, so this is our boom. Now we can plug this into here, and we can plug this into here. So then we're going to get our torque is going to be equal to 14.375 kilograms meters per second square, or not meters per second, just meters square. Negative 0.873 radians per second squared. So our torque is going to equal negative 12.55. Let's call it Newton meters. Yeah, that is our torque. That is not our final answer. That is our final answer. If there was no, actually, no, it wouldn't be our final answer then. We still gotta solve for the friction, not the friction. What am I talking about? Still solve for the kinetic, the coefficient of friction. That's what I meant. Still looking for the coefficient of friction. Okay. Now here's another formula we're gonna introduce right here. T equals R cross F. So this is the torque being applied, right? Actually, you can go one step further. Torque is equal to RF because it's only, there's no 2 digits like, let's say 6 I hat plus 8 K hat. There's none of that, it's just the 1. So we can just get rid of the cross and go right to multiplication. Now we have torque and we have a radius. So we need, here is our force. So we need F is equal to T over R. And the reason for this is going to be, that's the actual force being applied to it. Let me explain this. So we're actively using 71. Because of the coefficient, only 12.5, no, not that. Only this force is actually being applied because of the friction. So we need to find that force. So our F is going to be equal to our torque, which is causing the stoppage of rotation, negative 12.55 newton-meters over our radius, which is 0.5, which is, boom, 0.5 meters. So our force is equal to negative 25.1 newtons. So that is how much force is actually being used to stop it because of our coefficient of friction. We're pushing with 71, but only 25.1 newtons is affecting it. So now it's just simply if this force right here, this 25, is going to be equal to our coefficient of kinetic, because it's basically slipping, times, let's call it FA. So this is going to be our FA, our applied force. Okay. Now I'm gonna try to make this make sense. That's totally okay. I can actually do this first. So kinetic is actually equal to over FA. Kinetic is equal to 25. You can drop the negative here because the kinetic does not have a sign. They're both in newtons, by the way. Let's cross out. Equals 0.353, which is our coefficient of friction. So you can see that's what it is up here. Okay, so what we did, we have a rotating object that's being that has a force being applied to it, a torque being applied to it that's slowing down. So it's spinning spinning this way, right? It's spinning around this way. This force right here, this force because the rag is slowing it down. So we need to find that force that is slowing it down, which is right here. Or that torque that is slowing it down. And then using that torque, dividing it by the radius, we can find the force that is slowing it down. And now by using that force that is slowing it down and dividing it by the total force being applied, we can find the ratio of force being applied to force slowing it down. That's a lot. We went through mode of inertia. We had to then find our own angular acceleration, not acceleration, angular velocity. We then find our own torque that is causing this counter rotation, if you will, that stoppage, that application in the opposite direction causing it to slow down. Then we had to find, we did a lot right here. So we went over everything. I'm pretty sure that makes sense. But yeah, we can go through it again if you want. We found the moment of inertia because it's a rotating object. We got our moment of inertia. And we need to find our torque. And torque is equal to moment of inertia times angular velocity. We had, our unit was in 50 revolutions per minute. We had to get into radians because our unit is radians. We then used we then found the change in velocity over time by using the final minus the initial over the total time to give us our radians per second squared, or which we could then plug in against our moment of inertia to find our torque. Using that torque, we can then find the force of that torque in a negative direction, and then using that, we can find the relationship of the force being applied to the actual force causing this change. And I will say, doing this problem, after doing it again, it was definitely a lot easier because the first time, I don't even know how long I was working on it just to get my points. But yeah, it did not go as smoothly as I would say as this. It was just because you had to find a whole bunch of equations. You had to go for the most part, I was stuck in revolutions per second and never went to radians per second. That was my error, and that's obviously a common error that we make. And again, there's so many layers to this problem. You have to know your formulas. So yeah, it was definitely challenging then, but I'd like to say I have a pretty good handle on it now.